Hello physics students. So in the last video, I briefly mentioned how electricity, the flow of electrons, can cause heat to build up in a resistor or even a wire. And the reason for that is that as the electrons are moving past the atoms in an electrical component, they're colliding with those atoms, and those collisions cause the atoms to vibrate more rapidly. And vibrating more rapidly means the temperature's going up. In other words, heat is building up. But of course, we can put in a lot of heat or a little bit of heat in a given amount of time. So we can pump it in at different rates. The physics term that quantifies how rapidly you put in energy or take it out is called power. So that's the topic for today, power in electrical circuits. Now I want to remind you that, again, power is what we call a rate. This is an equation from the mechanics section of the reference table. We learned about it all the way back in the energy topic. Power is work over time, and when you do this, this is joules per second. What you get is a watt. And a reminder that this W does not mean watt. The watts is actually the power. So watts is over here. This W is joules, joules per second. How quickly energy is moving into or out of something is what we call power, a rate. Now, before I jump into the power in a circuit, because this is mechanics, before I move on, what I want to do is show you a couple demonstrations that I did earlier in the year, so time machine again, to show you so you could actually see the effects of power going into electrical circuit. Two demonstrations, so brace yourself, here you go. Today we're going to be learning about the power in a resistor or any electrical circuit. To illustrate the concept, I have a demonstration set up here for you. Now what I have here, which you probably can't even hardly see, is a very thin wire connected between these two alligator clips, which are connected to this power supply. Now the wire, I'm going to come closer and show you, is, as I said, extremely thin. So you see it next to my fingers here. It looks like basically almost like a hair. And it may look like bare copper wire, but it actually isn't. It's coated with something that acts like a resistor. Now normally we cover wires with plastic or rubber or something like that. This is sort of some kind of painted on material because the wire is so thin, they wanted to keep the insulation very thin. So what I had to do first when I set this demonstration up is I had to scrape the wire clean at the very end of that insulation on both ends so that the alligator clips would successfully make a connection. So right here, this is cleaned off wire at the alligator clips. What I'm going to do is, without any resistance in the circuit, I am going to turn this on and pass electricity through this. What you're going to see is that this wire heats up, and the way we're going to see the evidence of that is that it'll first begin smoking as that insulation burns off. So there it is. You could hopefully see that smoke. And now the insulation's burned off and the wire's glowing orange. We're basically at an equilibrium where the heat is radiating out as quickly as the power supply is putting it in. And when we're talking about rate of heat going in or out, really what we're talking about is the joules per second. In other words, the power. But so we're at this equilibrium, but if I crank this voltage higher, it'll pass more current through that wire, so the electrons going through the wire will slam into the atoms even more rapidly, producing more heat so fast that the wire will not be able to dissipate it fast enough. And then we're going to see something pretty dramatic happen. The wire actually melted. I melted metal with the electric current passing through. So that is a demonstration of power going in extremely rapidly, heating up the copper wires. Now, if I could keep the heat coming out as quickly as I was putting it in, the wire would not melt. And one substance that's very good at absorbing heat and pulling it away from wires is water. So this is another demonstration I'm going to set up here I got a little small beaker of water, and I'm going to place a big coil of that wire that I just melted, coiled up into the water, so that when I pass the current through it, the water will be removing the heat out of the copper pretty effectively. And then we're going to basically see that we could heat up the water through the electrical power. So let me submerge this and make sure everything's underwater so that the heat's effectively. Now what I'm going to do is turn this up, and let's see. Yeah, that looks good. Maybe 2.5 amps is what so I'm passing a certain amount of current through here, but it'll take a while for this water to heat up. So let's move on with the notes, and when we reach a sufficient temperature, I'll come back to this in a minute or so. Oh, before I do, looks like our water is boiling. So just a few minutes, and hopefully you can see that. The water is boiling because of the power being delivered to it, the electrical power. Instead of the wires melting, they're heating the water up and boiling it. So that's basically one application of this with heating elements. All right, so pretty cool. I melted metal with only electrical current in the first demonstration. And in the second demonstration, I boiled water with only electrical energy. So two dramatic demonstrations of power in a circuit. But of course we want to quantify, which means we want to be able to calculate exactly how much power is going into an electrical circuit. So we have here three different power equations. So it looks like one equation, but there's P equals IV, P equals I squared R, and P equals V squared over R, all put into one line for just convenience and sort of keep things compact. But these three equations have concepts loaded in them. Like, for example, the first equation, P equals IV, kind of makes sense. If I said, do you think more current would mean more power in a circuit? Most people say, yeah, it would. How about more voltage into a circuit? People say, oh yeah, that would make more power go into circuit. So this is pretty common sense. This is an interesting one here, that if you have a given, so two ways to look at this. For a given amount of fixed current, the more resistance, the more power, okay? That makes sense if I'm going to send, say, 1 amp into one wire, and it's very easy for that amp to flow. The wire won't heat up much. But if I send 1 amp into another wire, and there's a lot of resistance, they're going to really collide with a lot of atoms along the way, that wire is going to heat up because more resistance, more power for a given current. Another way to look at it is if, let's suppose you've got a given wire, so the R is fixed, then the more current you push through that wire, the more it's going to heat up, the more power you're putting into that wire. That makes sense also because you're tunneling more electrons into the atoms and making them hit, but with a squared relationship. So the current's more important than the resistance. Interesting. And then the last equation here, V squared over R, two ways to look at this one also. Let's suppose you've got a given voltage, like the voltage in your wall outlets is 120 volts. The more resistance, the less power. And that kind of makes sense. If I had a lot of resistance and I plugged it into an outlet, not much current would come out of the outlet, so there wouldn't be much power. But if I had a small resistor, so it was easy for electricity, and I put 120 and I put that in, then a lot more power because less resistance, more power for the same voltage. But the other way to look at it is if the resistance is fixed, let's suppose you take an appliance and you plug it into 120 volts, you get a certain amount of power coming out. But then you plug it into a higher voltage, same appliance, same resistance, same wires that it's made of. But with more voltage, the power goes up squared. So the power really builds up with voltage, the heat or whatever, the energy. So those are all the concepts in those three equations that are stored in those three equations. In addition to that, you might have to graph and create graphs with power and maybe current, and see that you would draw a parabola, There are a few example problems in the homework tonight. Now, the other set of equations is just if you take this and you solve for the energy, which is W in an equation, the energy delivered, it's power times time. A lot of power over a lot of time, well, that obviously is going to burn up a lot of energy. So work, if you solve for work, power times time, and then it's basically all of these three formulas with time slipped in. So you see I squared R times time, V squared over R times time. Okay, so pretty straightforward. Now, these are on the reference table. Oh, here it is. Both these sets of equations. So here we are in the electricity section, which is page 4 of the reference table. And you see right here by my finger, the first set power, the 3 equations I have, and then the work or energy is the 4 equations I have written on the board in a slightly different format, but you get the idea. All right, so what I'm going to do is one example. So let's take a look. Oh, let me give you a moment first if you need a moment to catch up copying these down. All right, let's take a look at the example. You got a tea kettle, operates on a home's 120 volts outlets, 120 volt outlets, heats water at a rate of 1500 watts. Now, first point I want to make, notice it didn't say the power. A lot of times in the Regents, they'll use the word rate instead of power, because if they said at a power of 1500 watts, it'd be easier to solve. People, oh, I'm solving, I know P. So they put this to make it a little more challenging. You have to realize that rate is power. Also, the wattage gives you a hint. So what are we asked to calculate? Part A, how much current does it need to operate? And part B, how long will it take to boil a cup of water with 140,000 joules? So let me create a pause to allow you to copy this down. All right, so let's move on. So the first thing that we have is we have the voltage, power, and we're looking for current. So we need to find a formula, power, voltage, and current. I won't come up with a reference table because we have it right here. It's this first part of the formula. Or we could have used P equals I squared R in another problem, but basically it's this right here, P equals IV. So we write out the formula. As always, we start by writing a formula out in the Regents. Put in the data. Again, 1500 watts is the power, 120 is the voltage. We solve for current 12.5 amps. Now, before I move on, I just want to make an interesting point. Tea kettles use a lot of energy. And just so you know, the wires in a typical bedroom, like maybe your bedroom at home, they get overloaded at 15 amps. Some of them are 20 amp circuits, but 15 amps. And you plug in the tea kettle, you're almost there. So a lot of people don't realize how easy it can be to overload wires in a house. A hair dryer is about this too. So you try and boil water and blow dry your hair, and you're going to completely overload your bedroom's electrical circuits. Okay, so interesting. Another interesting thing I want to just point out a little aside. The house I live in was built in the 1950s, and so as I was sort of looking at the circuits, I discovered that more than half my house was wired on one 15 amp circuit. 2 bedrooms, the living room, the basement, and the laundry room, all on one 15 amp circuit. I boil a cup of water, look at, I'm almost overloading 3/4 of the house's electricity. Interesting, because it got me thinking, why would they do that? And you start to realize, well, life back in the 1950s, no computers. Maybe you had one television in the whole house, but a lot of people didn't even have TVs. So what did you have? No computers, no cell phones, no iPads, just lights. So, modern era, we need more electricity, obviously, right? But just a little interesting, I went on a little tangent, but a lot of current just to boil water in a little simple tea kettle, electrical tea kettle. All right, let's move on so I don't get this too long here. B, how long will it take to boil the cup of water if it takes 140,000 joules to boil? Well, then we're going to use this equation, or we could have used this equation, same equation, and it would have been a little easier, less algebra if I used this one. But I decided to use this one from the mechanics just to remind you sometimes students make a mistake when they solve for the variable that's unknown in the denominator. So what they might do is divide both sides by 140,000 here, but you plug in the power here, the 140 is the 1,000 joules is the work. Before you do any dividing, you first have to cross multiply. 1,500 times t is 1,500 t, 1, right? This is over 1. 1 times 140,000. Then you divide by 1,500 and you get 93.3 seconds, which is about a minute and a half to boil. That's about right. A little tea kettle maybe wait a minute or so. So let me create a pause to allow you to copy this down. Okay, so and another thing I want to make a point, reminder, we talked about this in mechanics, all these times must be in seconds. Sometimes they give you minutes, so you got to remember if they say 1 minute, then you're plugging in 60 seconds for time. So, all right, so that's power, an example. What I want to do is go back to explain something that I showed you earlier in the year. Remember I showed you that clip of the helicopters bringing in the people to work on the electrical wires that were like 500 or 600,000 volts. And so those wires were such high voltage, they had to be on these giant telephone poles. All the trees underneath had to be cut down. And no one could climb up on a ladder to work on those wires because the electrocution, the lightning bolts would hit the trees, set fire, so they cut them all down. Or they would go through the person and vaporize the person and kill them in an explosion. So they had to go work on those power lines by delivering the people with helicopters. There were all these fancy procedures. I want to remind you that I'm going to show you that 3-minute clip just so you could appreciate the amazing technological feat to work on those wires. And then I'm going to explain, why did they have the voltage so high? Why not just make it a lower, safer voltage? Well, I'm going to explain. But first, I'm going to send you time machine to back when I had this running on my projector in my classroom. So, another time travel. Brace yourself.
I don't give two hoots and a holler about flying inside a helicopter. Put me outside. That's where I want to be. On the magic carpet. Back in the late 1800s, there was a gentleman by the name of Michael Faraday. He had a theory that if you enclosed a man in a metal cage and energized that cage at whatever voltage, the man would still live. The voltage would flow around him. I wear a hot suit. It's 75% Nomex for fire retardant and 25% stainless steel thread. And that metal thread means I have a Faraday cage around me. 500,000 volts pass over my body, but I can work without interference from the electricity. As long as the helicopter is isolated from ground, we have the ability to bring ourselves to the same voltage potential as the line, like a bird on a wire. Our pilots are very smooth. It's like they can read our every thought. There's such a hunger for electricity these days. Nobody wants to take lines out of service just to maintain them. I've had many people ask me, do you think what you do is safe? And I say, well, in our operation, everything that we do, every move that we make is thought of and rehearsed before, so it's as safe as crossing the street. It's not a job for a hot dog. There's only three things I've ever been afraid of: electricity, heights, and women. And I'm married too.
So, now I want to try and explain why those power lines, those wires, were up at 500,000, or I've even heard over 600,000 volts. Why not just make them a lower voltage to make them safer to work on? So here's a schematic of the electrical grid. Electricity transmission. Somewhere you have to have a generator. Now these generators, people don't want them close to where they live because they might be a nuclear power plant, which people are afraid of, or it could be something that burns coal, makes a lot of pollution, or it could be a hydro dam very far away wherever the river is. The point is you have to get somehow this energy over to the customers thousands of miles away, so you have these lines that run thousands of miles. But the problem is that wires, the longer they are, the more resistance they have. Sure, you can minimize with these other variables, but if you make the wires too thick, one, it's expensive, two, they're too heavy and they just collapse the poles. So thousands of miles makes a lot of resistance in these wires. That's going to mean that when you pass electricity, there's going to be heat loss. And the heat loss based on electrical current is I squared R. With this already so huge, the more current you have, the more these wires are going to heat up and radiate heat into the atmosphere. Means more coal has to be purchased by the utility company. They don't want that. They don't want to waste the energy into heat. So they want to minimize this power loss. And the only way is, since this is thousands of miles, they can't move the river closer or the nuclear power plant closer to the city. So this is fixed. The only thing they can control is to make the current as small as possible. But that's going to make less power delivered unless, to minimize the current, what you have to do, output here, is with this as small as possible, you need to make the voltage as big as possible to get as much energy over those wires with as little current as possible. So we try and make a tiny current. That was the reason why the voltage has to be so high, to make the current as small as possible so the heat loss is as small as possible. Problem is, if you deliver 500,000 volts into a house, there'd be lightning bolts shooting out of your outlets, electrocuting and killing people, houses burning down. You can't have that. So what you have to do now is make the voltage safe enough to go into a house. That's what they use, what's called a transformer. It changes voltages in an alternating current circuit. So we get this 500,000, a certain amount of power going into the transformer. And what we want is that power now to be transferred to go to the homes. So the transformer is going to take in power and then give out power. There'll be some heat, some loss in the transformer, but pretty much the energy in will equal the energy out more or less, minus a little percentage loss. So as I mentioned, from these thousands of miles, we've got a small current but a huge voltage. P equals IV. What comes out of the transformer is that the voltage gets reduced, so I drew the V much smaller here, but in the process you get a lot more current coming out of the transformer. And now the current is okay because the wires are shorter, they're just moving from one neighborhood to another. They're not thousands of miles long, maybe just a couple miles long, so we can handle the higher current and not have as much heat loss. So there it is. Maximize voltage to minimize current here, and then you reduce the voltage but you maximize the current that goes out to the customers, and overall you try and get this power coming out of the generator as close as to what's coming into the homes, and it saves the utility company money, increases profits, lowers the price of electricity, so on and so forth. All right, so let me create a pause to give you a chance to copy this schematic diagram down. Okay, so that's it. Power, just focused in on those equations that were on the first board here and the example problem. And that's the physics for today. And I hope you enjoyed. I hope you enjoyed the demonstrations and the explanations. And I'll see you in the next physics video.